So peat has silt size, not clay. So this clay size probably that the colloids things, yeah. And then we don't have sand in peat, sand side. Okay, so I'll give you some of the properties we found using our after doing some experiments. Bond post classification. Yeah, bonds, you do it by squeezing the peat itself, and you see the material that coming out, which is the water, whether it's murky or clear water. So the clear water means it's fibrous, it's new peat. If it's murky, then it's already mixed with all the colloids and things and become darker, right? So we tested it, and then we found out that it is about H7 to H9. Almost towards the end of the decomposition. Some says that working with peat, you don't have the certainty because peat today is not the same as peat tomorrow. But I think that's not entirely correct. Why? Because decomposition takes a long time. Yeah, according to literature, 1 millimeter of peat takes 1 year. So 1,000 years, 1 meter of peat. So how many meter of peat do we have in second round projects? So it takes probably very long time to create that peat. So so that statement probably not true. That hindered us to investigate peat, because if we have peat today and not the same as tomorrow, there's no reason we do the test or we do investigation. So that's not the case actually. It takes sometimes long time. In situ moisture contents about 500 to 1200. Okay, in mineral soil we rarely have 100%. This one with peat we even have more than 1000. So I will jump a little bit to the liquid limits. It's about the same. So what's the meaning of that? Meaning the peat that we have here is liquid form. It's not solid. So you'll find at site that the peat that we have is slurry in slurry form, in liquid, because it's even higher than its liquid limit, the water content that we found in situ. Specific gravity is very light, 1.5. Sand is 2.65. Water is 1, so it's closer to water than sand. Average particle size about 33 micron. Yeah, 33 micron, 75 micron is the sand. The smallest sand is 33 micron. Yeah? It's not as small as clay, but smaller than sand. In situ unit weight, this is a troublemaker. About 11 kilonewton kPa only. Yeah, kilonewton per meter cube, sorry. So I'll give you only a 0.6 or 1 effective stress per meter, 0.1 or 0.6 or 1. Yeah, if you deduct it from the water, if it is hydrostatic, very low effective stress. Fiber content 2.5, 11%, because it is separate, then you're gonna have less than that. Organic content almost 100%. So we don't have mineral in there. Yeah? Peat water, pH 4.2. 4.2 is very acidic, right? So less than 4, normally fish cannot live. Yeah, only probably snakehead fish. Yeah, the hardworm fish that's normally can live less than 4. Yeah, pH of 3 is lemon juice. So it's above lemon juice, but fish cannot live in our peat in overall. But probably some fish can live like snakehead. Plastic limit is very difficult to do plastic limit, and it's also not relevant. Why? Because the peat is the texture is totally different. You cannot roll it. Yeah. So, but some try their best. It's about this number. But if you reduce this, if you subtract this from this, it's gonna have very high number. So it's not something that we can interpret at the moment. Yeah? If we want to make analogy with clay. Okay, what about mechanical properties? Void ratio is very high, 8 to 20. Can you imagine that? Clay is probably maybe 1, 2, 3, but 8 to 20. So all peat range from literature 7 to 25. Yeah? Permeability 10 to the power minus 8 to 10 to the power minus 10. This is final permeability. You need to be very careful when you test. When you do permeability test at lab, wait for some times. It takes at least 2 hours in order to make things stable. So initial permeability of peat is very high. So you're probably higher than the sand. But when we talk about final permeability, the true permeability is very low, almost like clay. Compression index CC 4.3, 5.4. The CC for clay is about 0.19, 2.6 at the most. So we have 7 to 7 times higher compression index. We're going to compress 3 to 7 times higher than clay. C alpha over CC. So C alpha over CC is some sort of findings that majority of researchers agree on that, but not all, because some says it's a function of normal stress as well. But majority agree that it's about this 0.06. So we found it's about 0.05 to 0.06 CC over C alpha. So we can predict C alpha from CC. By knowing CC, we can know C alpha. So our C alpha over CC is 5 to 6 higher than clay. So our creep 5 to 6 higher than clay, the compression 3 to 7 higher than clay. So we can imagine the material that we are working with. Coefficient of consolidation about 0.2 to 3.1. Yeah, it depends on the amount of vertical stress that you apply. Yeah. I think Dr. Jim also discussed about CC over 1 plus E naught. What is it? So this is specific volume. So if you deduct that, it will converge nicely the curves, but it's not necessarily to be. I will show you later how that beneficial, but that's probably one of the things that you can make use of. Okay, so this is our C alpha and CC for Samarhan for our peak in Samarhan. You see here we successfully somehow get some undisturbed only at the superficial, a very shallow depth. So we do with PVC tube. So we just push it, and then take some material, but only for shallow depth. But for deep, probably we cannot do. So we compare that more or less, give us more or less the same. C alpha over CC 0.045 to 0.55, and CC is about this number. Okay. So undisturbed sample shows higher compressibility properties than disturbed. Be careful also. So if you get from a remolded test in the lab, then you don't use that. You have to think of that the actual one probably gives you higher compressibility. Undrained shear strength. So Dr. Jim says 0.4. I think I saw an August result. We got a 0.7. I'll give you there is a new research telling that what if you do that with the track shell, it might give you a misleading result. Surely I will give you one. Effective friction angle 33. I don't know why it's magic number. Effective friction angle 33, and then also the size of peat is 33. Apparent cohesion 4. Coefficient of lateral air pressure 0.2, 0.55 for normally consolidated. Yeah. And then this is the use of that CC over 1 plus E naught. If you divide it by specific volume, it will convert this and this. This is our study. This is the someone else. So if you do it, if you divide it by specific volume, this probably will converge. Okay? And then it looks more or less the same to us, although normally the NCL line and critical state line, normally they are parallel, but we found it a little bit focused, a little bit not 100% parallel because of probably there's some cementation or something else inside it. Yeah. So if you draw it, Q versus P prime, if you do track shell test, you probably know this, right? Critical state line and then tension cutoff. Sometimes peat, not sometimes, many peats, they can even reach this one, tension cutoff. What is tension cutoff? If you keep compressing the peat sample in the track shell, the pore water pressure inside the sample can be as much as the confining pressure outside. So what you're going to have is pretty much unconfined peat, but it still gives you Q, the diatric stress, right? So that's what we call tension cutoff. So what is actually happening is just tension. There's no compression, there is no shear, just tension. So that's what we call tension cutoff. Many peat reach this one, but our peat here is similar to clay. Yeah, it just a little bit go above the critical state line and go back. So meaning closer to clay in some sense. Yeah? Okay. So what happened? This is a recent paper from Muraro and Jomi. They are from Netherlands. Yeah? They have lots of peat research there. So what happened if you do if you do a shear strength test with triaxial, yeah, normally we have a porous stone at the top and at the bottom, right? So that actually will create problem. Why? Peat is very soft, so when it confined, it become very skinny, yeah? And then these two places where the at the top and at the bottom will become dead wedge. If you use porous stone is very rough. It's gonna grab that peat, eh? It's gonna make the top part become a dead wedge, eh? And the bottom part. It should not happen because we assume that vertical stress and horizontal stress is principal stress, right? Principal stress is the stress where at the plane where it gives you shear stress equal to 0. So we should not have that shear at the top and at the bottom and at the side as well. Eh? So this dead wedge will create problem. What problem? The pore water pressure is different. The pore water pressure here is higher than the one at the bulging sides. They check the moisture content after the test. They found it's different. Okay. So what happened? So look at this famous compressibility curve. Eh? E versus P, but it's not log here, just P. So you have NCL here. So if you have undrained test, triaxial undrained, for example, CIU test, it goes to the left, right? It's supposed to go to the left because undrained. There's no change in void ratio. It goes to the left and give you the CLL. This is the P. This is a normal effective stress here. But since we have different pore water pressure, it can go up here, B, or it can go down here, A. Give us higher P. Higher P means higher shear strength, which is misleading, right? Our shear strength, actual shear strength should be here. Yeah. So this one is this condition here at the dead wedge. Give us misleading higher shear strength. So what we do if we use normal triaxial procedure using porous stone, it can give us much higher friction angle. So you need to ask the consultant who's do the test if they have frictionless porous stone, that's fine, but I doubt they don't have. And then if that's the case, you need to correct. Yeah, correct. You plot this and then you correct. Or if you just use this research, they said that the actual 143, they got 45. So there is about 28% increase in friction angle. Yeah? So you need to be careful on that. Malaysian peat from direct shear test significantly lower effective friction angle from peat outside. So be careful on that. So don't just grab and extrapolate whatever you read from their research in temperate region. Our peat here is different again. All right. So what is the summary for our peat? Desirable part, higher friction angle. Undrained shear strength to ratio to effective stress, but be aware of end restraint. Yeah, the one we just mentioned. Undesirable, there are many. Yeah? High moisture content can be higher than liquid limit when in nature. Lightweight, low in situ effective stress, although high friction angle, but if we have low effective stress, then the shear strength will be low also, right? So this is become not good, yeah, if we have low effective stress. Acidic, so if you have a reinforcement, if you have a steel structure on top of it, that will be problematic. High in situ void ratio, you need lots of filling. Compressively 3 to 7 times higher than clay, 5 to 6 times higher than clay. So that's the problem we have. Eh? All right, so let's jump into alluvium. Right. Okay, so what is alluvium again? Alluvium is accumulation of sedimentation of particles through running water or flood. So we have lots of rivers in Malaysia, 1,800 rivers. One of the rivers is the longest in Malaysia, about 600 kilometers long, which is Rajang River, we know. But the longest one is not far from us, which is 1,100 in Kalimantan Barat, in West Kalimantan. So the catchment area is also double than our catchment area here. So what is the catchment area? Area that's surrounding that, where that alluvium will be created. Yeah? They're gonna accumulate alluvium in that catchment area. Okay, so why do we care about our alluvial soil? Because they are associated with soft soil. So according to the SPT test, we got most of them 0. Yes, just like peat, 0 SPT. So Sarawak alluvial was created during recent quaternary period, Holocene, Yeah, Holocene is the recent period. You look at geological time, Holocene is about 10 to 20,000 years ago. So it was created about 10 to 20,000 years ago. Early modern human lives, maybe Prophet Adam lives about that age. Yeah? So that's where when our alluvium created here, based on the thickness of peat, 1 millimeter per year. So about 10,000 years ago, it's about maybe 10 meter. We have peat here about 10 meter depth. So more or less, probably kind of agree with the data. So the problem is, since it is sedimentary soil, it might not be normally consolidated. It might be under consolidated. I'll show you this. Our soil here is probably under consolidated, with the fact that we have. So what is under consolidated? Still, the consolidation is still ongoing, due to its own weight. We still don't have overburden, but it's still consolidating. Both the pressure is still there. Does inherent anisotropy exist? So that's a big problem in sedimentary soil. Being near to water bodies, cyclic loading from the tidal. Our tidal here sometimes even more than twice, even 4 times a day. So we have a cycling loading towards our pile. So our pile may be subject to that cyclic loading. And then some activities, dredging, and then maybe scouring, but scouring is not that deep, but dredging probably a problem. Okay, so why do we care? Because we're gonna construct our bridge there, right? So we need to take care of our pile because it's gonna be supported by a pile, I believe, especially with the friction part. So the anisotropy that I'm talking about is this. So when you install a pile, when you insert a pile, so definitely the mechanism of soil surrounding it is something like this. So your sample has to be taken this way. Not the one that you take from Shelby tube or thin wall. It's vertical, horizontal, right? Vertical, but you take the sample horizontal. But if you want to simulate the actual mechanism, it has to be the opposite. You have to take both horizontal or vertical. This is the normal one, but this one is relevant to horizontal loading. This one is relevant to vertical loading. So you see here what mechanism we have here. It's not like track shear. It's not track shear, right? It's not direct shear. It's not torsional. It is direct simple shear. This simple shear. So you just simply shear it. So this is the best mechanism. Several researchers already decided that, already mentioned that, and no one argued. This is the best method. Direct simple shear. So if you don't have that here in Sarawak, you can go to JKR. JKR has that machine, and also we have that in Unimas as well. So don't worry. So we have the equipment in Sarawak right now. So the problem is lack of soil characterization of DSS. Why? Because limited availability of that equipment, and also the analysis is quite difficult. Because when you have track shear, your function, you have a more column, right? You cannot construct more column using DSS unless you know the horizontal stress. You don't know the horizontal stress when you do a normal direct simple shear test. And then when you draw deviatoric stress versus principal stress, you cannot do it with the direct simple shear because the horizontal is not principal stress. The horizontal is vertical stress. Be careful. So if you still think of that principal stress is not principal stress. The principal stress in direct shear keep rotating. It's not horizontal and vertical like in direct shear. It's different. Okay. So where do we take our sample? We take our sample here. Moralasa, and then Rajang, Batang Rajang, and Paloh. Three. Actually, we have another one here near Bintulu, Jepak. So where you're gonna install your bridges later on. So we have some sample already, and then when you extract, it looks like this. So like clay, brown clay because it contains organic material inside. So this is our classification. We found that it is sandy organic cell. It's not clay. Sandy organic cell. So therefore, marine clay is wrong. So when you call it marine clay, probably it's not correct. Sandy organic cell. It has organic content about 8.9% and PI 23%. GS 2.47, which is less than sand. Why? Because we have organic content, which is very light inside it. Water content 77%. Okay, so what do we do in order to know the issue, this issue? Yeah, so we take sample, so we extrude our sample and we take it horizontally and vertically and horizontally, yeah? And then we do our direct shear, simple shear test. We have 52 samples, specimens, yeah, that we tested, yeah. And then the depth from ground level, so we take it from SPT test, saturated unit weight, in situ vertical stress, and SPT value. You see here, most of them are 0. There's 2 here, 5.5 here, 12. Yeah, it's not that much. But majority is 0. Yeah, nothing we can get out of our SPT value. Okay. This is the direct simple shear test. So we have rings. Yeah, rings, and then we have sample inside, and then we consolidate, then we shear. Shear. So we record the vertical load, we apply vertical load, and then we shear, and then we record the shearing, and then we record the displacement. And then this is a typical results that we get. It's not the same as triaxial, you see. So if you are very vigilant, if you are very careful, triaxial is like this. Here, go up very quickly, and then slow down, diminish very slowly, compared to triaxial. So the behavior is more or less the same. Yeah, if we have low vertical load, it's gonna give you hyperbolic like this. If you have higher, then you're gonna have peak, peak but slowly diminish, compared to triaxial. This is pore water pressure. Yeah, pore water pressure. Pore water pressure doesn't show that much. Why? Because we do it very slowly. Yeah, we do it very slowly. So it also against what the earlier researcher about talking about direct simple shear test, where this one corresponds to the vertical stress. It's not actually. So this one on very minimum. This is the vertical load when we do under undrained, then the vertical load will decrease. This is the results. What we have here, so we compare the vertical and horizontal, the vertical and horizontal. This one is the peak friction angle. This one is the critical state friction angle. So we compare over consolidated, normally consolidated, and both over consolidated and normally consolidated together. And then we found that they are not different. The vertical and horizontal are the same, give you the same properties. And also critical state. Probably not clear, but you can go to the our paper later on and you can read and you can see the clear picture there. We also compare with if you probably use shunt shape or main, probably very famous, right? So they have correlation between OCR and shear strength, right? And then it's not the same as theirs. At the clay, it probably a little bit not as sharp as their results. So we need to be careful because the increase of OCR is not giving us as much as increase in shear strength. That's the meaning of this. And then this is the second modulus, shear modulus G. It increases with the vertical side, which is normal. It's normal like other clay. And then we are not satisfied with that. We do our we look at the SCM and prove that there's no anisotropy. Normally, when you look at SCM, if it has inherent anisotropy, the particles are aligned, aligned with horizontal respect to horizontal direction. We don't find it here. Okay, so these are the some of the results. The peak friction angle is about 23 degree. And then the directionality analysis, the SCM image showing that we don't have that inherent anisotropy. Now that was monotonic loading. So when we have a monotonic loading, what about cyclic? So we care about tidal effects and dredging and human activities where perhaps your pile will swing a little bit. If you can make sure that your pile doesn't swing, then this one has no point. But I'm pretty sure that your pile probably swing even a few millimeters. If that's the case, then you are in trouble. What trouble that we have? So we do a direct simple shear test under cyclic load. So what happened? So we target 135 mm. So the size of the direct simple shear is 5 centimeter in diameter and only 2 centimeter at height. So 0.35, if we divide by the height, so the shear strength is about 2%. Yeah, 2%. So 2% is this. 2% is in here, in an elastic part. Here is about 10%. These are the critical, this is residual. So we try at that elastic regime or region, and then this is about the peak, and then this is residual, critical or residual. And then this is the frequency, and we apply 80 kPa and 160 kPa normal load. So that this is a cyclic event that we do. So we do it like this, up and go, back and forth, back and forth. Okay, but prior to that, we do a normal odometer test to check what is the CC, CR, and E0. So pretty much like marine clay. So if some says that it perhaps the properties more or less like marine clay, correct? But it is not marine clay. So this is the results. And then this is the typical results. So we have 3 samples tested, and this is typical results. This is for 0.35. 3 millimeter, and then 8 millimeter, right? So what we see here, so when you see the loaded shear with shear strength, it goes like this, right? So when you do another cycle, it a little bit less steeper, less steeper, less steeper. So meaning the more cycle that you do, what will be the difference? The difference is the shear modulus, right? The second modulus, or the Young modulus, if you want to call it like the Young modulus. The brittleness is different, become less and less stiff. And then this pore water pressure. This probably is something to do with the speed that we do. If you do it in high speed, then the pore water pressure will generate. If you do it slow speed, then probably it's not that much. All right. So how do we calculate that shear modulus and damping? In the cyclic event, there has to be a damping. Damping is something that decay. So when you have a pure, there's no damping, it's just gonna repeat itself. There's no end. But if you have a damping, then it's gonna end. So initially like this, and then it's gonna slow down. So that's what we call damping. So the higher the damping, the higher it absorbs or decays. So this is how to calculate. Shear modulus is very simple. Shear strength divided by shear stress divided by shear strength. And then the damping is, you have to calculate the region that covered by that cycle, and then divide it by this. You can go to this paper. Shear modulus is not Young modulus. So be careful when you input that into a GeoSlope or GeoStudio or Plaxis. So shear modulus is not the same as Young modulus, but they are correlated. What is the correlation? So shear modulus equal to Young modulus divided by 2 times 1 plus. What is it? Poisson ratio. Poisson ratio is if you do a Poisson ratio test, how that material expand when you apply a particle. So Poisson ratio for soil is 0.1 to 0.5. So if you put 0.5, let's say here, so your shear modulus is 1/3 of, it's about 1/3 or 1/4 of Young modulus. So normally the softest soil probably around 5,000 Young modulus, like when you put in GeoStudio. So it's about that. Okay, so what we have, this is cyclic event, the cycle loadings from 0 to 30. Shear modulus, damping ratio. So if we keep on loading it, so what's going to happen? Our shear modulus decreases. The strength of our soil decrease. This is only 30 times. So how many times you think? How many years your design would be? And then how many times of fluctuation of loading that you're gonna expect that's gonna happen? Of course, if you see here, it diminishes slowly and become constant after some time. But you need to make sure where it become constant. You cannot just say 30. We did test just 30 because we don't have much time. We need to extend it and to see where it gonna become constant, right? Otherwise, your strength become overestimate. You overestimate. In fact, it has lower than that. Shear modulus also decreases. It's not a good thing. This sample number 2 a bit weird. Probably there's some error in it. I'm not sure, but I have to look back. But the damping ratio is the same. It also decreases here, but it's kind of messy here. But when we see sample 3, it again is the same as sample A, as sample 1. So meaning this probably the representative properties or characteristic of it. Okay. So when we compare with the cohesive soil, so our damping ratio and normal modulus is somehow at the bottom of it, at the bottom of that materials. Okay, so summary. What is the characteristic of our alluvial soil here? Desirable part, medium friction angle, it's about 23 degree. Before correction, low inherent isotropy. I don't know whether it's good or bad. But of course, it's a good thing because you only take either vertical or horizontal. You don't have to do both. Non-expansive. So when we put it underwater, it doesn't swell. It's a good thing. But undesirable, many. Possibility of existing excess pore water pressure. Possibility of existing pore water pressure. Why? Because the SPT value that you get is 0. Doesn't give you any shear strength, right? But we have the friction angle, 33. So where that friction angle coming from? Where that shear strength coming from? So I believe the existing pore water pressure is still there, so that we have very low effective stress. So we need to check that whether it's indeed has a remaining or existing pore water pressure. So how? So probably using a CPTU or other sensors that can measure how much is the existing pore water pressure inside that soil. Low shear modulus, can you see here? Very low. Low, it's about, if you multiply by 3, it's about 4,000, 5,000. Organic content, low specific gravity, reduction in modulus as cyclic loading increases. Okay, so you need to determine how many cycles that you're going to expect, and then how much is the shear modulus in that particular cycles. Reduction in damping ratio. Okay. Last but not least, this is probably the last page. General conclusion, tropical peat and alluvial soil show some undesirable characteristics. Need to be careful. We have more homeworks than normal soil, than residual soil, than clay soil. More homeworks than normally encountered residual soil, sand, silt, clay. In situ excess pore water pressure measurement is recommended. So probably use CPTU. Maybe it's just piezometer, you install it there. In situ and lab test need to be coupled. When you have in situ, you need to have another lab test to couple. And then the cyclic loading results show reduction in strength and damping ratio, which needs to be taken into account in your design. Okay, so thank you very much. Everything here is already published. There are a few that are already on the pipeline. So if you want to use the data, you're welcome. I think that's all. If you have any question, let me know. Thank you very much.
If there are any questions, if there is, please raise your hand so I can pass you the mic. So, if you ask questions, we can also ask Dr. Chief's session. Anyone else?
Kalau saya Yes, how under those and so on. We really have actually do all these lifestyle students activity distribution. This is going on.
Okay, with regards to existing or remaining water pressure, consolidated and consolidated, it happened in Singapore actually. There was I can't remember the name of the plant and it kills for the workers at that time. And it was found out that the alluvial soil that they have there is under consolidated. So what they decided at that time is plot based on the result from the land, where the increase of Japan, that just 3-0 there because there's nothing. So I believe because Singapore and our coast line is not that part of the time. And this is my fact. I haven't proven it to be true. But why is it us a low value of Japan? That we do SPT. It should be by some value, right? The way it's like it's you know that. But the problem here is that what the content that you check, since example the video is not probably presenting the actual content. So how do we compare what the actual content? You know that it's equal, then it might be because of that equal, but you don't find it. So I suggest you do probably test for check whether we have many test for water pressure because we have a structure that we're gonna put a power base so we have that water pressure. So that's why I think we need to be careful on that. And then with regards to test PSS, we have the PSS here in Sarawak already. Of course, scientific test you cannot do on site because there is no institute testing that you can do a static test for far. There are some bench here that develop to check scientific event, but just for lecture, but not for checking the action like that. So we still have to do static test in the lab. You want to make sure that your part structure can resist that static events. It's not about the value. The value can be anything, right? But the understanding, the engineer has some expectation when they are asked later on, they have this kind of knowledge so that they can defend themselves. So value can be. So if you are wrong in value, then we are wrong because you do. But you can do that, but you are wrong because you don't have knowledge. So the value that I'm giving here is probably the one that we get from limited amount of samples. So I would suggest if we do more and then we compare that.
Okay, so any more questions on the floor? There's my hands, I can pass the mic. All right, we have no more questions, so we will proceed. We'll proceed to the next pickup. So,
Thanks, Sophie and Dr. RCB. Our next knowledge sharing topic is the Geotechnical. Geosynthetic topic, fundamental and testing by our modern guest speaker, Marcus Jong Chin-Ju, and he's a technical services manager from Encounter Geosynthetic Asia. Marcus has over 10 years of experience in geotechnical and geosynthetic engineering, covering Asia and Asia Pacific regions. Marcus Yong graduated from the first class honors in his Bachelor of Engineering degree from University of Malaysia and awarded with the prestigious Professor Tim Pong Prize. He has also authored and presented several technical publications in international conferences. Marcus Yong was involved in the drafting of Section 5 ground improvement standard certification with the API Malaysia. And currently, it's co-supervising a university industry collaborated PhD research program with Monash University Malaysia. That's all IR Marcus job.
Hello, a very good morning to honorable guests, distinguished speakers, ladies and gentlemen. I'm Marcus from Encada Geosynthetics Asia. Currently, we are under a Stormax company. And personally, I'm also born in Sarawak. I'm from Kuching as well. So I stay in West Malaysia since 19 years old until now. So let's begin with the presentation today. So the topics of the presentation today is about geosynthetics, the fundamentals, the functions, and the testing of geosynthetics, in which I will cover 6 parts of the presentation today. The first part will be the fundamental of geosynthetics. The second part is the usage of geosynthetics for soft ground engineering. Third part is about the properties and testing, and I will focus on those properties and testing that we can carry out in the daily QA/QC laboratories. And then fourth, I will also talk about properties and testing, and they are more special. We are not able to carry out all this testing in our usual laboratories. It has to be sent to a specialist laboratories to conduct all those tests. Fifth, I will talk about PVD specification and discharge capacity testing. And lastly, I will summarize to you about the standard specification for ground improvement. So part 1, the fundamentals of geosynthetics. Geosynthetics are products. At least one or more of the components is made from a synthetics or natural polymers, and it can come with different structures used in contact with soil or other materials in geotechnical and civil engineering applications. For example, in hydraulics, in environmental engineering, in transportation engineering, and so on. So when it comes to classification of geosynthetics, it is primarily classified by using the appearance of the geosynthetics. An example, geoform has an appearance of form. Geostrips come with an appearance of strip, and those look like a mat. We call them as geomat, and geomat could be a synthetic geomat or natural geomat. Geospacer, geonet look like net, geocell, and so on. And if we have more than one subcategories under a single class of geosynthetics, then we will normally name it according to the manufacturing methods. For example, geotextile. Geotextile could be further classified to the non-woven geotextile that is made from a spunbond manufacturing methods. Knitted geotextile made from knitting method. Woven geotextile made from weaving methods. Likewise, for geogrids that you've seen in the market. So there is knitted or woven geogrids available in the market, in which we call them as a flexible geogrids. Then we have bonded geogrid available in the market, as well as extruded geogrids. Talking about geosynthetic barrier, they are named according to the raw materials. For example, polymeric geosynthetic barrier made from polymers, we normally call it as geomembrane. And those made from clay, we call it as GCL. And lastly, the last category is about geocomposites that comprise of more than one elements of geosynthetics in the structures. Give you an example, the PC geocomposite textiles is being made from knitting methods of polyester yarn onto a non-woven geotextile, in which the polyester yarn will give a reinforcement function and the non-woven geotextile will give a separation functions. PVDs is also classified as a geocomposite. It comprises of the drainage core and also the filter. So the objective of the filter here is to minimize the clay intrusion into a drainage core and cause the clogging to the water flow. Third is a silk curtain. And also those geocomposite textile that is meant for prolonged UV exposure. This is the range of products we call geotubes. It's normally for hydraulic application, in which we will have a tubes or bags or mattresses that permanently subjected to UV. And you know, geosynthetics can be deteriorated quite fast under prolonged UV exposure. And the purpose of geocomposite is to have the coarse fibers that can lengthen the service lifespan of the geosynthetic products. And geosynthetics, it's very important to pay attention to this part because this is the functions of geosynthetics. And geosynthetic design is primarily benchmarked on the functions of geosynthetics. And currently there are about 11 functions of geosynthetics that are available. It will keep on increase because due to the research and development going on in the geosynthetic industry. And this particular slide gives you an overview about properties and testing of geosynthetics. So the first photo here, this is about the physical properties testing, is the mass testing. And the second and third photos here shows to you a hydraulic properties testing, in which the second photo is the opening size testing, and the third photo is vertical water flow testing. And number fourth and number fifth, the photos here is about mechanical testing, CBR puncture, and tensile strength test. So why properties and testing of geosynthetic are important? We can look at it from two perspectives. From a manufacturer like us, it's important to ensure the product consistencies. It's important to have a statistic of our productions because some of the products needs to be reported to us statistically set values. And it's also very important for us as a practice for continuous improvement. Whereas from a customer perspective, it's very important to ensure the safety of the structures. It's about ultimate limit stats control. And also it's important to control the deformation of the structures, serviceability limit specs. And it serves as a good benchmark for sourcing by having the correct specification that stated the correct test standards. You can compare different products from different manufacturers in in an objective manner. So you can basically compare apple to apple. And these two tables summarize to you the properties and testing for geotextile and geogrids for the table on your left, and those for geomembrane for the table on your right. And you can see here, actually, they can be subdivided to a few categories. Mechanical properties here. So includes tensile strength test, CBR test, interface friction test like direct shear and pull out test. And then hydraulic properties, opening size, vertical water flow, in-plane water flow. For geomembrane, don't have hydraulic properties because it is totally impermeable. Physical properties like the mass and thickness, as well as endurance properties, or what we so-called as long-term or durability properties. Here. And the durability is a critical subject in geosynthetics studies. Durability is studied on the changes of functional properties with time. And as an engineer, we must ensure there is enough margin of safety, or we commonly name it as factor of safety when it comes to the geosynthetics design. So I draw your attention to the figures on your right. So number 10 here is the design life. And the orange color line is the required functional properties from before construction until the end of design life of the structures. And the blue colors here is the available properties from geosynthetics. It's important that the blue color must be always higher than the orange color at any point of time, whether it is at the end of design life or during the intermediate time, with sufficient factor of safety. And it can be represented in two ways. First is to have a ratio between the blue color line to the orange color line. Alternatively, you can use the ratio between the time to failure to the end of design life. And talking about the design life, and this is the table from BS Code of Practice. It gives you some indications about the design life for different types of structures. For example, a more short, medium terms application like basal reinforcement on ground, the critical time is actually at the end of construction. And after the end of construction, the soil will start consolidate and gain strength, and slowly you can notice the reduction of tensile strength in geosynthetics. However, for a more long-term application, for example, geosynthetics on piles, this is talking about 60 years or 120 years of design life, in which you can see the strength of geosynthetic is in fact increased with time, and is the highest during the end of service life. So when we design for our engineering structures, we need to use the long-term design strength to design, not the short-term design strength. So how do we derive a long-term design strength? We use the characteristic tensile strength divided by the creep factors here, installation damage factor, and environmental factors, and that's where we derive to our long-term design strength. So these slides, I basically summarize to you how do we carry out the assessment for geosynthetics. First, we need to define the purpose, the design life, the environmental challenge of the engineering structures. Secondly, we have to ask ourselves, is geosynthetic option is a feasible options for these particular structures. And if it is suitable, then we get to select the correct type of geosynthetic with the correct or most relevant functions, and then carry out the detailed engineering design and evaluation, identify the required properties and testing, and choose a grade with a sufficient margin of safety, and compile everything into engineering drawings and a formal specification. So I give you one example here. This is our previous projects in Chiang Mai, Thailand. It's about a road widening project that was built with the reinforced soil slopes concepts. So the geogrids is being laid layer by layer. And the facing here is using the green facing. And talking about this particular case, the purpose here is about the road widening, and the design life is 120 years. The criteria here is to ensure the safety and the tolerable deformation of the structures. And how do we assess whether it is feasible? It got to be constructible, it got to be economical, and also timely. And in these various projects, the consultants select a Miragrid GX geogrids with the reinforcement function, which is the most relevant function here. And then the key properties here will be the long-term design strength. In a more layman words, we can define it as a tensile strength at 120 years from now. And through the engineering analysis, for example, a slip circle analysis, so we got to ensure there is sufficient factor of safety. Normally for reinforced wall slope is about 1.5. For embankment, one of the speakers just now also mentioned is around 1.2 to 1.3. And lastly, compile everything into engineering sections and product specifications. So by then I have completed on the part 1 of the presentation. So now I'll move into the geosynthetics for soft ground engineering. So transportation infrastructures, these are the 6 most common transportation infrastructures that we normally see in the market or in the environment. There will be unpaved roads, lot supporting platform, paved roads, railway, seaports, and airports. They all actually share the similarities. They are normally founded on one of the following. They can be built directly on ground if the ground is a good ground. And if the ground is not a good ground, then we have to carry out the subgrade stabilization. And it can be also built on embankment. So why do we need to build the structure on embankment? Because we want to raise up the structure level above the flood level, or we want to connect the particular structures to the bridges structure at the higher elevations. And to build it on embankment, we can build the embankments that sit on ground. We can also consider to build the embankment that sit on piles. And lastly, we can also consider to build the structures on viaduct. And viaduct must sit on piles. And the primary objectives in transportation infrastructure design included the pavement or track structure stability. Here, in which for roads, we got to ensure there is sufficient thickness and a good quality of the asphalt course, the base course, and the sub-base course. For the railway, we got to ensure there is sufficient thickness of ballast, sub-ballast, and so on. And we also got to ensure the foundation stability. For example, the embankment stability will be very much depends on the slip circle failure or foundation extrusion. And if our transportation infrastructure sit on retaining structure, then it's important to ensure the stability of retaining structures. Last but not least, safety and comfort of ride. Safety and comfort of ride depends primarily on deformations, and deformation is mainly attributed by differential settlement. And of course, differential settlement is a very critical topic. It's also a very difficult topic. I remember a few years ago when Professor Jihan from US, University of Kansas, came to Penang and KL to give a talk about soft ground engineering, and one of the audience raised the question, how can I predict the differential settlement correctly? And the answer back to the audience from Professor Jihan is that I can become a millionaire if I know how to predict the differential settlement correctly. It's in fact tell us that it's not easy. It's a very complicated topic. So the strategy to deal with differential settlement is back to limiting a post-construction settlement. So what is meant by post-construction settlement? So I will explain to you in these figures, and you will see a difference for post-construction settlements between the structures that sit on ground, embankment that sit on ground, as well as embankment that sit on piles. So the y-axis here is the sediment. The x-axis is time. And this is a timing whereby we start the embankment or the structures constructions, finish of embankment constructions. This is the time when we start the pavement or rail track constructions. And this is the time when we open our structures to the traffic. So if we build the infrastructures on ground directly, as soon as you open to the traffic, you will have the traffic-induced settlement. In pavement engineering, we name it as RUT deck. In rail engineering, we name it as rail settlement. And before that, during the construction of the pavement, the base course, sub-base course, the ballast, etc., you will also have some settlement. And when we add these two settlements together, this becomes the post-construction settlement for the infrastructure that built on ground directly. All right, then we now move to a second case. If we build an embankment on piles, pile embankment. So first of all, pile will also have some sediment, especially those friction piles. And embankment field could have some compression, depends on the gradations. When we add these two sediment together, this is the total sediment for the pavement or rail track that sit on a pile foundation. Do we concern with the total sediment values? Probably not. We are more concerned about the post-construction sediment value, because before you start the pavement construction, whatever sediment on embankment, we can always come back and relabel it and make sure it is totally flat before we place our pavement or rail track. So you can see this become a total post-construction sediment for pile embankment. So now I move into the third case, embankment that sit on ground. So again, there will be some small amount of embankment field compressions, plus the embankment soft ground foundation sediment. And this become a total sediment of embankment that sit on ground. And this is the real concern, the total post-construction sediment. So why do we need to use PVD to surcharge it? Is because we want to ensure this particular total post-construction sediments is within the design limit. So now if I summarize them again into the same graph, you will see there is a different magnitude of post-construction sediment for different types of structures. And this table is from the Professor Zhu Jian from Nanyang Technological Universities. It's a general guidelines on the post-construction sediment limits that we should comply with. For example, a highway pavement at general area should be less than or equal to 300 millimeter. The bridge approach area got to be less than or equal to 100 millimeter. For the airport pavement, if you notice from the flight information during the landing of the aircraft, the speed of the aircraft is almost 200 kilometers. So it's faster than a normal car that we use on roads. So that's why the sediment limit is also more stringent here, less than or equal to 50 millimeter. When it comes to high-speed rail that travel more than 300 kilometers per hour, then the sediment limits became 20 millimeter. And those maglev trains that can easily travel up to 500 kilometers per hour and above, then the sediment limit is definitely less than 2 millimeter. And this limit also determines on which type of structures that we decide to construct. For example, maglev train will be mostly sit on viaduct, sit on piles, because with 2 millimeter, it's very difficult to be achieved by a normal ground improvement method. So now I move into the brief explanation of soft ground, and I won't cover more details about this part because the previous two speakers have covered them very intensively. Basically, when we talk about soft ground in a general perspective, it's referring to soft clay or peat soil, and they normally have the instability problem as well as the sediment problems. So how geosynthetics can help to resolve these soft ground engineering problems? First, you can consider using high-strength woven geotextile to prevent slip instability of the embankment. In this particular application, reinforcement is the primary functions. So that's why in the technical data sheet, we always look for tensile strength, a long-term design strength. And at the same time, a secondary function, which is less important, but still relevant, is a separation function. That's why you also see more application of geotextiles for this application rather than other class of geosynthetics like geogrids. It's less common because geogrid don't separate. Second, PVDs for resolving the sediment-related issues. And the primary function of PVD is drainage, with secondary function of filtration from the filter jacket. Second applications, pile embankment. The most common pile embankment is built by using reinforced concrete slabs. Actually, you can also consider geosynthetics as an alternative towards these RC slabs, and it is proved to work throughout many years of experience as of now. Again, the primary function is reinforcement. Secondary function is separation. Third is the embankment that sits on a kind of ground that's subjected to the subsidence. For example, a limestone area, whereas you may expect some cavities or subsidence That's where the geosynthetic can help you to prevent your structures from a quick collapse into that subsidence, give you a double assurance. Again, the same functions here applied, reinforcement as being a primary one, and separation being a secondary function. Fourth is the subgrade stabilization. So during my previous slides, I have mentioned that for the infrastructure that sit directly on ground, if it is on a soft ground, it's very difficult to construct. And it's very difficult for the vehicles or the live lots to move. And in this particular instance, we need to consider subgrade stabilization. It could be a stabilization geotextiles or geogrids that provide a mechanical stabilization. And you can also consider a chemical stabilization by a cement or lime. And talking about the subgrade stabilization geosynthetics, in fact, in the market, there are 5 types of geosynthetics that are suitable to the subgrade stabilization. Each of them having their own advantage. And the first 3 referring to a geotextile in the textile form. And the 4th one is a geogrids in a grid form and geocell in the cell form. So you can see for the subgrade stabilization, basically that's the function that we need for geosynthetics. Separation and filtration function on the hydraulics consideration. Drainage and confinement functions on the mechanical stabilization consideration. And lastly, in a very unique subgrades, if you expect a lot of moisture that is in place for the structure that you are dealing with, and you can consider a moisture management function. So non-woven geotextile typically is very good on the hydraulic side, but relatively weak on the mechanical side. Woven geotextile being more balanced, it can separate, it can filter, at the same time it can reinforce and it can confine. Weaking geotextile is the most balanced one. It can separate, it can reinforce the structures. It can also work as a moisture management products. Geogrid and geocell are very strong in terms of the mechanical strength, but there is no separation. So to use geogrid, you can consider the consequences is that you got to use the additional layer of non-woven geotextile, and that's where the cost and the time consideration may come in. So now I show you 3 types of geotextiles for subgrade stabilization. This is non-woven geotextiles. This is a mechanical stabilized woven geotextile. And this is a mechanical stabilization and moisture management geotextile, in which there is a wicking yarn here to absorb the moisture and drain off the moisture. And the very last application of geosynthetic for soft ground, I bring up this application, we call it as soft pond capping. So it's being used for those very soft ground. How do I define as a very soft ground? I remember the previous speaker also mentioned about the under-consolidated soil. So this is basically for this kind of very, very soft. It's in fact, the behavior of the soil is very close to the water rather than the soil. And it's actually also very dangerous for us as a human to walk in this particular area because we will sink down directly. I actually visited one of the project sites in Singapore on this soft ground, a soft pond capping, and I have to wear the life jacket to go into this particular project area. And you can see for this kind of soft pond capping, how soft it is, as soon as you start the filling, you can see the surrounding site start to heave up. And we really got to anchor the perimeter of the pond properly. And this is one of our projects in China. It's a very big pond, ex-mining pond. And in this particular application, you need a balance between reinforcement, separation, and filtration functions from geotextile. And typically, geogrid is not suitable towards this application. It's not easy to use geogrid. And what we need is a medium to high strength geotextile, and it could be a polypropylene geotextile. It could be also polyester geotextile, depends on our objective. If we want the geotextile to float above water to ease the insulation, then we got to use polypropylene. But if our objective is to sink down the geotextile immediately after we lay the geotextile, then we got to use polyester. And also we got to consider the pH condition of the particular soil. And when it comes to a single layer of laying, the seam strength become particularly important. A normal seam strength that we can normally achieve on site may not be sufficient. That's why normally for soft pond capping, it's talking about the factory big panel seaming. So that means it's pre-seam in the factory. Normally we can achieve up to around 70% and above for the seam strength. And then we carry it or we transport the big panel to the project site directly. So that's where I finish the part 2 of my presentations. So now I'll move into the part 3, the properties and testing. And this part you will see all the properties and testing that we are able to carry out in the normal laboratories. But before that, let's look at some of the criteria to be considered as a good laboratories for geosynthetics. First, this is a GuideLab certificates from Geosynthetic Institute from US. It's a specialized institute that works in this geosynthetic industry. And this certificate got to be renewed per annum basis. Second certificate, this is ISO 17025 certificates. In Malaysia, it's represented by Department of Standard Malaysia. This serves as a basic certificate for all laboratories, including geosynthetics related laboratories, including all the concrete, steel testing related laboratories, as well as the medical and so on. And of course, you may like to consider about the information about the manufacturer. For example, this is an ISO 9001 certificate, a quality management system. And this is a manufacturing license from a manufacturer to prove that that there is a factory exists in Malaysia, and could be also a Buatan Malaysia certificate from a Kementerian Perdagangan Dalam Negeri dan Harewan Pengguna. And then you may also want to consider the product certification license. For example, currently we are certified by CIRIM for few range of our products, and this is a certificate for high-strength woven geotextiles, in which nowadays we actually can issue the test certificate and test report under the CIRIM logo. That means CIRIM actually certified for all the manufacturing process, from the raw material input until the finished products, inclusive of the laboratories. And this is the certificates from JKR. This is, in fact, not a certificate, but a kelulusan product from JKR. And this is for our non-woven geotextile, for our woven stabilization geotextile, for high-strength woven geotextile, for PVDs, for Miragrid GX geogrids, as well as for the polyfelt PEC geocomposite textile. And normally when it comes to properties and testing, this table summarizes to you a common QA/QC test that we can carry out in the laboratories. Normally in the geosynthetics test laboratory, got to have a temperature between 20 degrees Celsius plus minus 2. The relative humidity between 50 to 70%. And geosynthetic sampling normally has to be carried out in a way to have the full width of geosynthetic row times the length. And the length could be different. For example, non-woven geotextile, whereby you wish to test more properties, not only tensile strength, but you're also interested in vertical water flow, opening size, then you need minimum 2 meters of length during your sampling process. For high-strength woven geotextile, that is concerning mainly on the tensile strength, so 1 meter typically is sufficient. For PVDs that has many properties got to be tested, we need to sample around 15 meter minimum of length. And the length will be increased if we wish to carry out more and more properties tests. And the first test is the physical properties. It's a mass testing, and there is ISO 9864 and STMD 5261, pretty similar. This is to know about the mass of the particular sample, and the sample has to be pre-cut to the specimen size of 100 centimeters square. And one value is reported to the average of minimum 10 specimens. Second is also a physical properties. So the diameter of the pressure foot is around 56.4 millimeter with a 25 centimeter square of area. The test result got to be reported to the average of 10 specimens. The ISO test method will take reading after 30 seconds, whereas STM test method will take reading after 5 seconds. So there is slight difference in between the test result if you carry out it according to either ISO or STM. Normally, STM you will find it thicker because the reading is being taken only after 5 seconds, whereas the ISO test method will compress the product more, so that's where you will see a thinner when it comes to the thickness properties. Third is wide width tensile strength test, and is actually referring to the mechanical properties here. This is one of the most common and most important tests, and it can be according to ISO 10319 or STMD 4595. In which you can see in terms of sample size and testing is pretty similar between the test standard. The only difference is on the strength rate, in which the ISO will carry out the test faster and the STM will be slightly lower. And normally the test results difference is quite negligible between the test standard, unless not to say unless, except for those a very, very super high strength product, then you can see some difference. And the test result from this test is suitable towards the design process. Steam test. So if you remember, just now I'm talking about the soft pond capping and emphasize about the importance of the steam. And that's where we can also carry out the steam test according to ISO 10321 or STMD 4884. And you can see to do the steaming, we can do a factory steaming or we can do a on-site steaming. And typically there are 3 types of steam. The common one will be a prayer steam. A more efficient one will be a jet steam or butterfly steam. So it depends again on the application and on the products. Second, mechanical properties, CBR puncture test, ISO 12236 and STMD 6241, they can consider identical in this particular test. So it's similar to the CBR test that we carry out on soil, or for the best course or sub-best course and so on. It's about a 50 millimeter diameter of plunger that try to puncture through the geotextiles. And now I move into the hydraulic test. This is the opening size testing according to ISO 12956. And this is what we call as wet sieving methods. It's used the granular soil. Because of using the granular soil and wet sieving, so that's why this test is not sensitive to the temperature and the humidity difference. However, this test is very time consuming. We need around 1 day to obtain a result for this test. If you want to consider a faster test, then STM D4751 is the faster test. You can complete it between around 30 minutes, I think, around there. But of course, the disadvantage here is that it is more sensitive to the changes in temperature and humidity. And it is not using the actual soil, instead it used the glass beads. So the second hydraulic properties, vertical water flow. This is talking about how much of water that pass through vertically across the plane of geosynthetics. And ISO 11058 and STMD 4491 are pretty similar in this particular test. And when we carry out this test, it's very important to predetermine the hydraulic head because we want to compare objectively the quality of products from a different manufacturers. We got to fix the hydraulic head first because the 50 millimeter result and the 100 millimeter results could be quite different. And SCM normally reporting in the unit of second powered by -1, whereas ISO reported in the unit of liter per meter square per second. So the third hydraulic test here is about the horizontal water flow. So the previous test is about how much of water go across the plane of geosynthetics. But now we are interested into how much of water that move horizontally in plane of geosynthetics. And you can use ISO 12958-1 as well as STMD 4716 to measure the water content. And these are the test standards explanation. They are very much similar. With the exception of 4716, you can only take the reading beginning 15 minutes, whereas ISO, you will take the readings after 10 minutes. So now I will So now I will also briefly explain to you those less common standards. Grab test, for example, this is STM test standards. It's used by the American Society of Civil STM of Civil Engineer, but it's actually not recognized by the ISO committee for a reason that ISO committee think that these tests do not provide the uniform lots on the specimen. If you can see here, the specimen width is around 100 millimeter, whereas the gauge length is only about 15 50 millimeters. So it's less representative. The test strength test is also by the ASTM committee. Likewise, it's not recognized by the ISO committee because the test strength will only happen when you have the initial cutoff on geosynthetics. And that is what we want to avoid at all costs. And it's very important to note that not all geosynthetics are suitable to carry out trapezoidal test strength tests. Okay, so for an example, non-woven geotextile, you can carry out the trapezoidal test strength test because the fabric structure allows you to do that. But for high-strength woven geotextile, in fact, there is no way to carry out the trapezoidal test strength test. Reason because the high-strength woven geotextile is typically made from polyester. And the polyester nature is that the surface of polyester will be very smooth. So you got to cut it and do the test strength test. Basically, you can't get any result because it will naturally slip against the yarn. So this is very important. Rod puncture test is a smaller scale of CBR puncture test. Nowadays, it's no longer being adopted for geotextiles. It's only stay in geomembrane industry. So this slide summarizes to you those obsolete test standards for geosynthetic industry. This is the summary from the ASTM committee D35. It stated that the Mullen burst test and the rod puncture test is no longer suitable to geotextile. And not only the committee is mentioning about this, it's also clearly being mentioned in the test standard itself. For example, this is a rod puncture test standard 4833. You can see it's stated as index puncture resistant of geomembrane and related products. And it is recommended in the clause 1.3 that the geotextile or geotextile related product should be tested to CBR puncture test, STMD 6241. All right, I also include 3 properties, the endurance properties in this section, because these endurance properties are those that we can carry out in our either laboratories or outdoor research area. So this photo shows you the ongoing PhD program, the collaborative program between Pankada and Monash University, Malaysia, to assess on the UV resistance of the geotubes range of products. And in this particular project, you can see here there is a UV sensor here that constantly record the accurate UVA and UVV of the environment. And there are 3 range of products being tested. One is the coarse fibers types of products. One is a normal woven product, and another one is an enhanced UV woven geotextile. So the good thing about this test is the result is very accurate, but the disadvantage about this test is that it will take a very long time. For example, this PhD program will target to carry out the research for 3 years on the outdoor UV studies. So if we don't have much time, we can consider to use the laboratory UV test. And as far as laboratory UV test is a concern, there are 2 test methods as well. Number 1 here is from the European norm EN12224. This is the machine. And it actually simulates the UVA 340 lamps at 340 nanometer of irradiance. And the exposure time, one cycle is about 430 hours, which is around 18 days. and it's equivalent to around 50 megajoules per meter square. And roughly the 50 megajoules is converted to around 2 to 4 months of the general Asia environment in the outdoor condition. But this correlation could be varies from project site to project site due to the influence from the UV, the humidity, the rainfall, etc. And the second test from STM is called as STM D4355. It's using a xenon arch as a light source, and it simulates 52 megajoules of meter square radiant exposure in the outdoor, and it's roughly equivalent to around 3 months of outdoor exposure in Florida in US. So by then I've completed on the part 3 of the presentations. So now I'll move into the part 4 of the presentation, which is also on properties and testing, but all these tests can be only carried out in external laboratories because we got to have a specialized equipment to do that. And normally all these tests are very costly, are very time consuming. So I start with the easiest one. This is the wicking capability test. Currently can be carried out by the SGI Testing Services Laboratories in Georgia in USA. And this test is to measure under a zero hydraulic gradients, how much of water that can move in plant here, and how much of water that can move against the gravity. And this is to assess the capability of moisture management for the wicking geotextiles. And second is about the direct shear and pull-out test. So why do we need to know about the direct shear or pull-out test from the soil with geosynthetics? It is because during the particular failure plan, for example, this one, you can see the failure plan actually shear on the interface between the soil and the geotextile. So we got to use this. We got to know this coefficient and enter it into the engineering design process. And in this particular regards, we also need to know the pull-out capabilities of the geosynthetic with soil to determine whether we do have sufficient pull-out length in our structure. So this is a direct shear test, ISO 12957-1 or STM equivalent of D5321. It's very similar to a normal direct shear test that we carry out on soil, but we actually change one side of it, become the solid base and put on the geosynthetic sample. And then we shear it off and see what is the coefficient. And secondly, this is a pull-out test box. As you can see, the test box is around 5 feet of length. The height is around 1 feet, and the width is around 2 feet. And we will place the geosynthetic specimen. We will place the geosynthetic specimen in the test box, and we try to pull the specimen up from the test box. And this table summarizes to you the interaction coefficient that you can use if you design by using a Miraphite PET geotextile. If you are using other manufacturer geotextile, then you got to take it. Then if you use others brand of high strength woven geotextile, then you got to request the interaction coefficient from them to carry out your design analysis. And it's very important for reinforcement application, retaining wall, retaining slopes, embankment, all that critical applications. We need to design by using the characteristic tensile strength So what is meant by characteristic tensile strength is that the manufacturer has to report to the statistically safe values. So what does it mean from an equation perspective? The manufacturer got to use the average value minus 1.64 of standard deviation, and this value become the reported values. So that's why normally if you use 200 kilonewton product, for example, if you test the product should normally have around 210 and above because of this reporting system. And this is a requirement under the VS Code of Practice, as well as requirement under the American FHWA. And this is the creep test. Like others construction products, concrete, steel, geosynthetics also has creep. And the creep got to be assessed from a creep rupture perspective for an ultimate limit stats design, and got to be assessed from a creep strength perspective for serviceability limit stats design. And normally creep strength tests can be carried out to a conventional method, ISO 13431 or STM equivalent of STMD 5262. This is a conventional creep test. And you can also consider using an accelerated creep test according to STMD 6992 under certain requirements. First, it is important to have a minimum of conventional tests that has been carried out for more than 1 year. And secondly, the result from the conventional test got to be very consistent with the accelerated test. So with these two conditions that come together, only we can use the accelerated test. So if I summarize to you, the long-term design strength of the structures that we are dealing with has a design life up to 1 million hours, which is close to more than 100 years to 120 years and above. But we cannot test the product up to 100 years. So the conventional creep test normally will test the product up to around 11 years, and it serves as a very accurate result. But if you use the accelerated test, then you got to have a minimum of 10,000 of conventional tests, plus the consistent accelerated test values. However, some professional group like ASCE, American Society of Civil Engineers, allow only 1 log cycles of extrapolation. That means as a minimum level, the manufacturer got to test the product up to 11 years and above. And ours Mirafi PET reinforcement geotextile is basically way above 11 years of testing as of now. So the second long-term test is about insulation damage. So insulation damage is considered much quicker compared to the creep test, but it got to be carried out in a large-scale perspective. There is a few specialized laboratories that can carry out this testing. For example, HGI test lab in US, TRI test lab in US. So what they need to do, they got to have a proper arranged test site with the steel plate and then lay down the geosynthetics. And before that, they got to lay a predetermined soil and well compact the soil. And then they lay the geosynthetics and then another layer of soil above the geosynthetics, and then use the compactor to achieve around 90 to 95% of compaction. And then extract the geosynthetic and carry out the testing again to determine how much the strength loss due to the insulation damage. And the test standard here is that you can do it according to STMD 5818 or BS 8006-1 Annex D. However, ISO 10722 quick test method is clearly stated by this document that it is only suitable for the index test. It's not suitable to use to derive the reduction factors for geosynthetics. And some of the manufacturers do use this test standard to derive the reduction factors, and we have to be very careful on that. Third is to assess on the environmental factors, and to assess that on polyester-based products, we get to assess on the hydrolysis, and it get to be 4 cycles of assessment, which is up to 112 days. And the end result of the assessment must be more than 50%. And this is the correct one. And we got to also test the molecular weight and carboxyl end groups of the polyester yarn to determine the crystallinity of the yarn. And the result here got to be more than 25,000 for the molecular weight and less than 30 for carboxyl end groups. If these 3 requirements are being satisfied, we can conclude that the product is predicted to be durable for a minimum of 100 years and above in the natural soil with pH between 4 to 9 and the soil temperature less than or equal to 25 degrees Celsius. So it is not suitable if the soil temperature is higher than 25 degrees. For example, in some part of India, sometimes our client will request a much higher temperature reduction factor. Some of the places like Chennai could have the soil temperature up to 35 degrees Celsius. And that's where the reduction factor also could be higher. And also taking note on the pH range, not all geosynthetics are suitable to a different pH range. Typically, to say, whatever less than pH of 10, typically high-strength woven geotextile have no problem. But of course, not to be too close to the lower boundary. But when the pH is go beyond 10, then it could be a consideration. And you got to contact the manufacturer to know the reduction factor that you can use for your particular design. So by then I have completed on the part 4 of the presentation. Bear in mind, all these tests could be very expensive. For example, the creep test is around 30, the initial cost is around 35,000 euros. And every year we got to continue the test for a minimum of 11 years. And every year is talking about close to 8,000 euros of extension. So it's very expensive. Maybe it's too expensive. So the installation damage could be up to 30 to 40,000 of USD. The environmental test could be up to 10,000 of euros. So it will be very costly. It will be very time consuming. Normally you can't do the test on the client side. It's normally the manufacturer got to do the test and present to you the reports. So now I will move into Hello? Okay. So now I will move into the part 5 of my presentation. It's about the PVD specification and discharge capacity testing. So this topic has been requested by the organizer to explain on the variance or on the importance of PVD specification. I will go through with you. Okay, so how does PVD work? I think it has been pretty well covered by the previous speakers. So what I want to summarize to you is that without PVD, the rate of consolidation is proportionate to the vertical permeability. or conductivity of the soil, and it's also indirectly proportional to the foundation depth. But with PVD, it is faster because it became directly proportionate to the radial hydraulic conductivity, and also indirectly proportional to the horizontal spacing between PVDs. And of course, increase in the rate of consolidation will result in the increase of foundation shear strength. And you can consider to use this in your design, and this got to be verified also by the actual soil test results. And partial penetration of PVD is always not recommended. And there are few airports in the world that experience the constant sediments due to the partial penetration of PVD. So it's not suitable. Singapore, in the current average soil depth, the PVD has been installed to around 30 to 40 meters. And in a specific area, the deepest one can go down to around 60 to 70 meters. So they will not install it partially. So we should not install it partially. And PVD being quite a simple product, but it has the most complicated specification among all geosynthetic categories. And it's the most difficult product to manage, frankly speaking. And from a business point of view, PVD is about a volume business, high volume, but it's a low and super competitive environment for these PVDs. And normally to install PVD, you will use some metal shoes. This is to anchor the PVD in the soft ground. And I personally summarized the PVD specification in year 2015, whereby I start to take over the PVD's product management from management direction. And that's where I see a very, very widely variable specification across the world. And you can see from the UK to China to Malaysia to Singapore to Hong Kong to Australia, they are different, especially when it comes to discharge capacity. And that could be different in terms of the hydraulic gradient. That could be different in terms of the pressure. That could be also different in terms of the values. Likewise, for filter jacket, they are also very different. So that's why in year 2007, European norm in 15237 has been published to so-called to clear off or minimize all these confusions. And these are the requirements from EN 15237 on PVDs. Basically, the tensile strength got to be more than 1.5 kilonewton for composite. Elongations, less than or equal to 10% at 0.5 kilonewton. And at the failure got to be more than or equal to 2 kilonewton. The filter got to be more than 3 or 6 kilonewton per meter, depends on the depth of the soil, depends on the condition of the soil, and also some others requirements. And these are the details of the test standards. And I would like to also draw your attention to one of the actual field tests in Singapore at the Pulau Tekong site, whereby the depth of PVD is around 32 to 36 meters. And the researcher actually measured the actual forces in PVD during the passing of the top row, during the insertion into the ground, as well as during the pull out. And what they found out is that the greatest force is being recorded during the insertion phase, and the highest one could be up to around 1.7 kilonewton. So that's why in PVD, whereby we have the joint got to be in so-called joint correctly, so that the joint itself have the sufficient strength against this insertion force. And the general tensile strength of our PVDs in Tenkara, we control it to be more than 1.8 kilonewton, included those seam or joint area for the medium to high range of PVD. But for the low range of PVD, we can't. And the previous few test sites for the filter geotextile, the PVD's filters recorded the highest as 1.4 kilonewton. If it converted back to per meter width for geotextile, it's around 7 kilonewton per meter. So that's why in Singapore specification, it needs the geotextile to be more than 7 kilonewton per meter. Geotextile for PVDs. And there is a lot of question talking about the discharge capacity test, whether it should be a straight test, whether it should be a kinker test or bucket test. And in year 2007 and in year 2015, two test standards actually cover for these particular doubts. You can see this is the extracted PVD from the actual site in a vertical forms, and there are some buckling or kinking happens. And according to the EN 15237, the kinkered discharge capacity has to be taken into consideration when we estimate more than 15% of sediment. So in a layman term, if you have 10 meter depth of soft soil and your sediment is more than 1.5 meter, and that's where you need to start consider about bucket test. Below that, perhaps it's not so important. Again, in ISO 18325, this test standard has been published in the year of 2015 to clear off a lot of inconsistency in the discharge capacity test. And before that, actually, the ISO committee auditor also came to Tenkara to have some discussion with us. And the discussion, and the objective of the discussion is that there are too many inconsistencies in the PVD specification. So that's why they want to publish the one that can clear off all this inconsistency. And that's why in year 2015, they published this newest test standard to resolve all this issue. And it's mentioned that in a less compressible soil, for those sediment less than 20%, you can actually consider of not looking at the bucket test. But of course, after a discussion with JKR back to 2 years ago, so we agreed to put a limit at 15%. So this graph summarizes to you a general pattern of discharge capacity that you will obtain under a different pressure and under a different geometry. The straight line, the discharge capacity will be always higher than the kinkered discharge capacity. And at the lower pressure, the discharge will be always higher than the higher pressure. So now I'll come to the other most complicated properties, discharge capacity. So I will go through with you one by one by looking at the test standard itself. The very original discharge capacity test is back to the year 1999 and 2000, ISO 12958 and STMD 4716. And these two tests only cover for the straight test. They don't cover for kinkered test. And generally, this is how we derive to the discharge capacity by using the volume of water times the correction factor for temperature divided by the second, how many seconds. So in which we obtain the volume of water per second. The STM test method mentioned that the reporting got to be in a meter cube per second or meter cube per second dash meter. So mainly is this one, or transmissivity meter square per second. The ISO mentioned that the unit should be in a liter per meter per second or meter cube per second. And That means these two standards mention that it got to be divided by the width. And that's not all the case. And then after that, in year 2003, STMD 6918 published two methods, method A and method B, to evaluate on the bucket test or Kinkert test. And surprisingly, the units are very much different, because the method A mentioned that it got to be in meter cube per second, but method B got to be in a meter cube per second, but further divided by I. So when the result is further divided by I, that's where the variance will start to appear. Presume the I is 1.0, then you don't see the difference. If the hydraulic gradient is 0.1, that means the end result that you obtain will be multiplied by 10. So it's again hard to compare a different test method. And then EN 15237 in 2007 mentioned that the discharge capacity should be divided by I. But it has been disagreed by the latest ISO committee. In 2015, they come back to a conclusion that there should be no any, the equation shouldn't be divided by the width. The equation shouldn't be divided by the hydraulic gradient, so that we can compare apple to apple for all the products. And then the second complicated issue is about the Kinkert angles. STMD 4716 and ISO 12958 do not have the Kinkert angle. STMD 6918 method A adopted a 45 degrees from the vertical line. So this is a Kinkert angle alpha. So STM method A adopt 45 degree, whereas method B adopt 70 degree. Very big difference again. And it has been corrected by ISO 18325 in the year of 2015. It has to be 60 degrees, around 60 degrees. And that is a representative one. And we have recently purchased this test equipment, and we are still setting up the test equipments. It will be ready by the end of the year. And this test equipment can test for both straight and kink geometry. And the general hydraulic gradient recommended fall between 0.1 to 1.0. And the vertical pressure recommended is 200 kPa for straight test and 120 kPa for bucket test. And the test duration is pretty long. It got to be tested for 60 seconds. Sorry, it's 360 seconds, which is 1 hour, 24 hours and 7 days, which is good. But again, it's not also very practical from a manufacturing point of view, because that means the test equipment got to be occupied by a single product for a very long time. So we are still considering whether we should follow the previous test standard, which is around 15 minutes. We think that it will be fair enough to use 15 minutes, because one of the tests taking for 15 minutes, and one result we got to carry out 3 tests, which is already around 1 hour to derive for one result. If let's say we put a specimen day for 7 days, that means in 7 days we can only test one product. That will become very much impractical. But we are still considering, and we will check further with ISO committee on their opinion as well. All right, this graph is summarized by Professor Chu Jian in year 2017. It's actually give you an equation and a graph to consider, so that you can avoid the influence of wear resistance in your PVD's design. So by then I will move into the last part of my presentation. I'm still on time, another 13 minutes, so I can finish just nice before 12:45, or could be faster. So I actually, together with a few industry players, we are being invited by Public Works Department in HQ to participate in this standard specification for ground improvement beginning to year 2017. And finally, this standard specification was published in the year of 2020. And I briefly go through with you some of the finalized specification. The table on your left is the specification for non-woven geotextile. There are 4 grades of non-woven geotextiles. And if you can see here, basically we streamline the test to only tensile strength test, CBR puncture, and con drop test. And in terms of the hydraulic test, we only use the permeability at 50 millimeter, no longer hundreds or no longer others, but 50 millimeter. And in terms of opening size test, we consider that some manufacturer can test in ISO, some manufacturer can test in STM, and some manufacturer can test both. So that's why we allow both. And as you can see, the test result for the STM and the ISO is very far different as far as this opening size is a concern. UV resistance we also consider for both EN and STM standard to be more than or equal to 70% for non-woven geotextile. For high-strength woven geotextiles, the first thing that we do is to add back the characteristic tensile strength words. This is to impose to the manufacturer that they cannot publish average value, because published average values is very risky for the structures. And we also add in the 5% stiffness. This is to minimize the movement or deformation of the structures. And third, we control also the long-term design strength to have a minimum limits. And these limits are being able to be achieved by a common manufacturer in Malaysia. And we have the short notes here to add on that this limit, this long-term design strength got to consider creep, insulation damage, environmental factor, and so on. And whatever tensile strength more than 800 kilonewton, actually you can see here, spatial design and specification should be discussed with the designers. Come to PVDs also, we streamline the specification and we have put in 2 types of PVDs. The type A is for a normal soil condition. Type B is for the more critical soil condition. For example, the insulation depth is more than 25 meters, or we install in kind of a more highly compressible soil, or if we use the vacuum preloading that can exert more loading on PVD, then we will go for type B. So I think it's come to the end of my presentations. Thank you very much for your attention. And if you have any question, please feel free to ask.
Thank you so much. There is a question from the online team. They say that, hi, Mr. Marcus. Thank you for a very informational presentation. It is permanent RTBAR is an effective and evenly distributing the stress used by the traffic. However, with provision of geosynthetic materials for power embankment on soft ground, no RC ground, how can we ensure mushroom effect and undulating surface will not occur? Okay.
So this question is about the power embankment design, and this is a very precise question. In power embankment, at all cases, we should avoid mushroom effects from happening. And how can we avoid that? Is that we got to have the sufficient thickness of field above the geosynthetics to avoid that. And BS code actually give you one equation. The minimum depth got to be more than 0.7 times S times the clear spacing between the power caps. And if you want to really go to the safe extreme, you can adopt as conservatively as 1.4 times the clear spacing between the power caps to avoid that things from happening. Yep.
Okay, then question from the door. Yes.
Yes. Probably. See, what that is.
This part. This part. That means the PVD is here, here, and these two are 60 degrees. We can actually change the angles of the test equipment. If the particular client needs a particular project to be tested to that angle, then we have to look for the way to modify the equipment. It's possible, as of what I know up to now, but this new equipment, because we still haven't finished the setup progress yet, so probably I can only verify to you by the end of the year. But it's something that is possible because we just need to change this angle. You means in the it doesn't represent the actual site, right? Okay, noted. Yeah, I mean from our perspective, we can. Yeah, this test equipment cannot. Yeah. Mm.
So before you step down from the stage, I would like to invite Mr. Dikazwe as the unit head of CTRU to give a token of appreciation for you as a speaker coming to this first session of the sharing technical. I would like to invite Dr. Jim to come up front to receive his token of appreciation. Okay. Thank you, Dr. Jim. Thank you, Mr. Marcus. Okay, ladies and gentlemen, we are already ending our first session. However, just to let you know that our lunch is not here on this floor. Our lunch is at level 1, the Imperial Garden Restaurant. So you may proceed over there to get your lunch shortly. And is there any other announcement that you make?
Online, we need to feel that also. And we have to live and produce and mitigate before that.
Okay, let me reiterate that. Before you entering the second sharing session, please re-register yourself with all the emails so that you can get your CPD points. And also for those online, you may also have to really put up onto your forms again to resubmit your forms again for the second session. So ladies and gentlemen, thank you so much for the first session. So we will proceed and adjourn to lunch and we come back at 1:30. Yeah, thank you. 1:30.